Great. All right. Hi, everyone. We hope you've all been having a great droidCon so far, and thank you so much for making it to our talk today. Just to quickly introduce ourselves, my name is Tasha, and I work on the user growth Android team at Tinder with my colleague Meha.
Hi everyone, I'm Meha. Tasha and work closely together. It's been almost 4 years now, and it's been an exciting journey to work. For us professionally, we have learned and grow so much. And also this is my first time presenting in the conference, so I'm very excited to be here and also a little bit nervous. Um, so we want to start off by acknowledging that there is a convergence across different platforms. It is an exciting time to be a mobile developer as technologies and patterns start to unify. Frameworks can share a lot more functionality than they previously could. With Swift UI on iOS, Jetpack Compose on Android, Reactive, React Native, Flutter, everything from web to mobile is trending towards a declarative approach when rendering UI. With declarative approach, we see that UI is a function of state and state is a snapshot of UI at that point of time. With this, let's take a dig at imperative UI. We are used to dealing with explicitly modifying our UI when something needs to change. And that is opposite of being declarative, where we don't explicitly modify UI elements. Imperative is do everything yourself and also describe how to do it. Declarative is describe what you need to be done and don't tell me the steps. And unless starting a component or app from scratch, chances are that if we want to introduce a declarative components into an established app, we might have to move a few things around. So in the imperative style, you would explicitly tell the component how it should look by explicitly modifying it. Here, both the data flow and the control flow are coupled. Let's take a typical example where we show a loading screen, and after a successful fetch, we show the list of conversations. Most of the time, this is how we configure a view imperatively by changing its properties. We have two functions here to change the UI from loading to loaded. And in each function, we are making explicit changes to the individual views to toggle their properties. In contrast, with declarative programming, you need only to describe what the component should look like, not how it should change. So, inherently, declarative UI has the potential to be platform agnostic, whereas imperative does not. So, if we were refactoring the previous example to be declarative, the first step would be to compile a state object to describe what we want to see. This encapsulates the properties that will change into a data class or a sealed class. With the construction of a state object, we are starting to look a little declarative. To finish the transformation with Jetpack Compose, we might end up looking at something like this, where our state object is used to only render the components that need to be rendering at that moment in time. And so the goal here is to be able to compile the state object that describes what the UI should look in the snapshot of time. If we are looking to introduce a declarative compose component into an existing app that does things very imperatively, chances are that it might not be seamless unless the setup is able to accurately describe what the component should look like at any point in time.
So, declarative rendering in general demands a bit more determinism and organization than we might have been able to get away with in the imperative world. This kind of made us wonder about what would it take for an existing imperatively based app to start hosting more declarative components. So we started to explore this from the perspective of a small app, which we call Space Library. It's a relatively simple app where you can search for images through the NASA Image Search API, and the search is executed as you type. It exhibits a three-screen navigation that includes a splash, an image results screen, and an image details screen. Throughout the presentation, we'll be referencing this app as we break down some ideas around structuring things at the presentation layer to satisfy both imperative and declarative rendering. The way we approached this was to work backwards from the perspective of declarative rendering, seeing what needs we'd have to satisfy and exploring architectures that might be a good fit for that, but that would also offer some extra organization and modularity. Our goal was to see how far the presentation layer could be split up into pure business logic and pure rendering, so that we could render the app in two separate flavors. One rendering with Android views and the other rendering with Compose, both sharing the same business logic. If you look at this, it's kind of similar to an approach taken with Kotlin multi-platform projects, only in this case, we're trying to serve two styles of UI frameworks instead of separate platforms. Doing this exercise really helped us understand what we could do with architectures that render UI imperatively in anticipation or in preparation of introducing more declarative components. To frame it in terms of a data flow, what we were really trying to see is what would it look like if the rendering layer was just an implementation detail, agnostic of imperative or declarative UI, while still keeping the business logic common to both rendering implementations. Through this exercise, we wanted to explore different architectures and sort of work backwards. So we ended up looking at some unidirectional architectures and also consulted some modular architectures like Viper. And through all of that, we kind of identified some main concepts that really helped us balance imperative with declarative. Looking at the presentation layer specifically, we might consider a breakdown that looks something like this. Obviously, the first concern would be to understand how to represent data needed in order to render a declarative UI. And so we'd be looking at how to identify states and properties first. Next, we need to understand how to reason about business logic, such as user and data layer interactions, in order to update the representation of our UI. And so we'd be looking at transforming such data to state. And finally, we will need to reason about how state could scale with added functionality. And for this, we will look into scoping state into different hierarchies. We'll go through each of these for the remainder of our talk. So let's begin with the first one, identifying states and properties. Properties are things that don't change over time. We can use the search bar here as an example. Its visibility and the text change listener don't change over time once they are set. In contrast, states are things that do change over time. If we take a look at the same component again, we see that the text inside this, of course, does change over time as the user types or if the user clicks the clear button. Translating this into code, our Android View implementation might look something like this, whereas our composable might look something like this. Here, we really want to point out this distinction between properties and states. On the left, with the Android Views implementation, we offer a more explicit distinction, whereas on the right, the declarative UI framework really allows us to have both in the same lexical vicinity. Speaking of states, two other important distinctions that we must note: stateless components and stateful components. Stateless components don't manage any internal state. Taking one of the items now in this list as an example, each item is configured externally and does not change over time, therefore it is stateless. However, in contrast, stateful components internally manage how they change over time, and their states can suffer mutations. Now, taking the entire screen as an example, the screen as a whole can exhibit several states: a loading, a loaded, or an error state, in addition to the query text itself changing over time. If we look at a stateless component first, talking about the image item in the list, both in the case of Android View and Compose flavors, we can see that we're really just setting two properties on this component, the image and a click listener, and nothing else is being set in this component, specifically that changes over time. This component can be considered to be stateless. A stateful component, on the other hand, would refer to maybe the fragment that handles everything for the entire screen, and a high-level composable that does the same thing in the composable flavor. Naturally, fragments and high-level composables or high-level declarative components are stateful because they are high-level, and they are intended to manage their screen state via view models, perhaps. For big components like these, making them stateful might of course make sense intuitively. After all, they are in charge of all their inner components. But for smaller components that are stateful, there could be cases where statefulness presents some issues. If we have a stateful component whose state needs to be read or written to from an external component, or whose state in fact drives multiple components external to it, we have a case of shared state. Shared state can typically be a little awkward because it leads to a case where both the stateful component and the external component need to keep copies of the state in sync with each other. With declarative frameworks, however, there is a concept known as state hoisting, where the practice is to lift the shared state and the mutator up into the closest common ancestor of where that state is shared. Once state hoisting is applied to a stateful component, we end up with a stateless component. Now, classifying properties, states, where a state must or must not be hoisted can seem somewhat subjective or even ambiguous at times, depending on our context. However, there are some basic questions and guidelines that we can go through to make more informed decisions. If we determine that the data of our component is a state, that is, it changes over time, we can then ask if the caller needs access to that state. If the answer to this is yes, we can then decide to hoist that state up by allowing the caller to set and mutate it. And then we'd end up with a stateless component whose state got hoisted. However, if the caller didn't need to read or write to that state, then we needn't worry about hoisting it at all. In fact, that state can be handled internally by that component, and that would keep the component as stateful. Going back now, if we actually figured out that our piece of data wasn't a state and did not change over time, we're probably dealing with a property. And in this case, we can decide if the caller needs to set it externally or if the component needs to compute it internally by whatever means. Let's take a look at what would happen with these concepts from a code perspective. Let's say we have a view on the top left here that represents the search input bar and a composable on the right that represents the search input bar as well. And we can see here that the view on the left is managing its own text and mutating it. But it also wants to allow external mutations. It also wants to allow external components to read that state. And this makes things awkward because now the external component would have to keep its representation of the text in sync with this component's representation of the text. On the right now, if we keep this state intact within the composable, it can get awkward if an external component needs access to it. However, if we apply state hoisting here, what we would end up getting is that for both cases, we would allow external reads and writes of that state without the awkwardness of keeping two copies of the same thing in two different places. By making the state and its mutations the responsibility of the caller, this component now as a whole becomes a lot more versatile. So with some of these guidelines, you'll probably start to identify what the properties of our component or app are, what the states are, and what needs to be stateful and what needs to be stateless. Next, let's look at how the state, if we do identify state, how will that state mutate over time?
So, what can mutate state? User interactions can change state, such as from the sample app, you are taken to a detailed image screen when you click on an item from the list of images. State can also change because of the data layer interactions, where here a user interaction causes data to load asynchronously, which then resumes with some sort of success or error result. For changes like this, we might consider a general unidirectional flow, where events are passed to a view model. The view model then updates a state representation of the component for every interaction and forwards it to a rendering component. All the business logic is pre-compiled before rendering occurs. And right away, we see that our rendering layer becomes an implementation detail. If events and state mutations were to get complex, things could easily get out of hand. Still, there are some options to organize events and mutations further, as we will see. Typical unidirectional flow is described like this, where multiple events from views mutate states that are then handed back to the view. However, with some ideas laid out by Redux, MVI, events or intents and state mutations can be organized further by grouping together all the interactions and designating a component that is a state reducer solely to handle state mutations. States are then immutable, and every event generates a new state which will represent snapshots of the rendering layer.
State mutations are referred to as reductions in these unidirectional architectures. And if we were to extract these state reductions out of the view model and into a separate component, our system might end up going from something like this to something like this. And here, what we're trying to do is we want to group together events into one pipeline and isolate state reductions to a designated component. In practice, if we have a case like this, where our view model is in charge of the state mutations or state reductions, we might end up with something like this. Since state mutations are essentially just functions that input states, events, and output other states, they can easily be their own isolated component. This reducer component, in this case, just lives in the state object, but it could easily be its own class or own component. The one benefit of this is if transitions change, or if your idea of state transitions change, then the view model itself need not be updated. By introducing events and a state reducer in this manner, we'd be reducing the view model itself into pretty much just a store for the current state, with the added benefit that it can survive configuration changes, of course. But what about data layer interactions involving persistence, involving network? Where would those really fit in? Right now, the view model is resembling just a store for current state, and perhaps we'd want to keep it that way and avoid giving it any more responsibilities. In order to do that, though, we'd have to avoid directly connecting the view model to the data layer. To get some more insight into what we could do with this, let's consult another architecture, the Viper pattern. We might have seen this pattern used alongside MVC, MVP, all of the M stars, especially it's used on iOS. It does resemble MVC, MVVM, and the like, but the hallmark here is it exhibits a lot more modularity. In particular, for our interests, it defines an interactor as the only thing that talks to the data layer. The interactor's role here is to transform data into whatever the presentation layer needs. If we consider the presenter to be analogous to a view model, then we might consider the interactor for our purposes. The interactor is also agnostic to whatever clean architecture abstractions that may lie in the data layer and beyond. So if we were to bring this component into our flow, we'd end up with something like this. Here, the view model's primary role is still just state storage. And now we can start to identify a secondary feature of the view model as being a pass-through for events and states. Going back to the code now, let's take a look at both our fragment and our high-level composable that represent the image result screen. Both use the image search view model, and we can see what the data layer transformations might look like if they're hosted directly in the view model. If we introduce an interaction to the picture, however, all we'll be doing is moving that transformation into the interactor so that it becomes the interactor's role to handle the data transformations in order to satisfy the view model's needs. And as we can see, the view model is now just storing state and passing data around to other components, including the interactor and the reducer. Back to our data flow here. Let's say that this constitutes one stateful system. What would this look like if our app complexity were to grow in terms of screens and functionality? And that's where we will look into scoping state into hierarchies.
For simple apps, one flat state system that handles navigation and screen state might be enough. But as complexity grows, we might see that app begins to demand some sort of hierarchical approach to states. A single screen app might just need one stateful system to manage the single screen, whereas a complex app with many complex screens, like on the rightmost, might benefit from a hierarchy of state systems where navigational state is the outermost layer. How would we conceptualize that hierarchy? In order to start scoping states that get too large or complex, first, identify which components operate independently and which operate in tandem. Second, pull up shared state into closest common ancestor. And lastly, each state system should only contain the minimum amount of data needed for its role. Taking the sample app as an example, let's start examining from the lowest layer up. On this screen, the search input bar might operate independently from the search results content because a user can type faster than we had want to fetch images. But at the same time, they are related because changing the input would trigger the change in the results. So we want to consider the input bar and the image results as being somewhat related but not nested. Zooming out a bit now to the entire screen, at the screen level, we establish the relationship of both component states from the previous slide because the screen is the closest common ancestor of both components. The technique we discussed earlier, known as state hoisting. Lastly, if we zoom out completely from the perspective of the whole app or activity, we arrive at the highest or the navigational layer. Here, the navigational state only needs to care about where to go and what its screen needs to begin its job. If we recall Viper from earlier, the router here is given special consideration as the component used by the presenter to handle navigation. The idea of a router comes into play here when we talk about the highest level navigational state. In general, with navigation, the highest level component provides the screens with what they need to be independent and manage their own state. The navigational state system is starting to look like the idea of a router. Here we have two simplified implementations of navigation for both Android views and composables. Looking at this as a whole, we can see that the basic idea of navigation applies both when dealing with Android fragments and composables. At this level, the only thing of interest is figuring out where to go and how to give the destination the data it needs to be initialized with.
For most multi screen apps, the highest level state would be navigational, where the only concern would be how to route and what arguments those routes may need. Screen state would be the next level down, and often screen state just involves stitching together the hoisted states of its constituent components. Lastly, the highest level of detail would reside at the component level, where components such as a check button, a radio button, or a text input bar can exhibit different states over time. More often than not, components at this level would usually have their state hoisted because their state would need to be shared by components that reside in the same hierarchy as them. After we've made a quick tour of each of these main points, let's review how the app, the Space Library app, is scoped at the moment. The outermost layer here deals with navigation, and by its very nature is of course stateful. It's represented by a view model and a state. Going the next layer down, we're at the screen level now, which is also by its very nature stateful. We have two screens to deal with at this level. One is the image search and the other is the detailed screen. And so we conceptualize two view models that deal with each of these screens, as well as two states that represent each of these screens. Going now to the innermost layer, we have components. And here the components would basically be represented by the query text and the image results states. Since these components are related though, their state needs to be kind of shared from something that sits above them or outside them. And because of that, these components states get hoisted up to the level of the screen, and these components themselves remain stateless. For a simple app, imperative or declarative, the presentation layer might still look something like this. We would need a component to handle mutations of state over time. We would need a component that would store the current state or the current representation of the UI. And then lastly, we would need a layer that just performs rendering. If we were to add a bit more complexity to this though, such as data layer or network interactions, we might need to throw something like an interactor into the mix. And here, the other components' roles don't change at all. It's just that we're adding another component that is able to cause mutations to that state. If we were to get even more complex, and let's say we added screens and navigation, we'd end up with a hierarchy of these stateful systems where routing sits at the very top, routing to each screen and providing each screen with the arguments that it needs to start managing its own state. And we can see here that at each layer, we're trying to scope the state and the state mutations only to the component that needs it. So in a sense, we are applying state hoisting both at a micro and a macro level. Now, these strategies offer advantages for both imperative and declarative rendering, as we found. By better identifying states and properties where state needs to be hoisted, both declarative and imperative rendering can be reasoned about more easily. It also prevents cases where components are arbitrarily made stateful and they're unnecessarily introducing complexity of managing their own state when they don't really need to. Next, having dedicated components to mutate and interact with the data layer makes it easier to spot bugs and edge cases during reviewing state mutations. And when data layer interactions are involved, if there needs to be any change with how the data layer interacts with your stateful system, the fact that you've isolated all that complexity to a separate component means that the components outside of that need not change as often as they would otherwise. Lastly, the idea of scoping state to almost to the extent where it reflects the hierarchy of the UI itself, starting at the navigational layer all the way to the component layer, it allows our presentation layer to, one, remain faithful to the representation of the UI so that it's easier to reason about, of course. But in addition to that, it's way easier, of course, to maintain separate stateful systems or separate scopes rather than allowing a small number of stateful systems to grow into monoliths as complexity arises. If we take a look at all of this together, we might say that the states we model, starting at the macro all the way down to the micro level, really just end up reflecting how our app or UI is structured. And if we think about it, we just really do end up with the idea that our whole app is a function of state, regardless of how we might want to render it. Because it's interesting to consider rendering as implementation detail in this way. And this abstracts out concepts of platform or frameworks and just leaves us with this small equation that could represent a whole app. Feel free to play around with the space library sample mentioned here. And there's another sample available as well called the Art Randomizer that exhibits a slightly simpler functionality. It exhibits a functionality that involves less navigation and more statefulness at the screen level. And that's all, everyone. Thank you so much for attending, and we hope you found this useful. We'd be happy to take any questions over Slido.
I can read the question.
Yeah. Oh, I think it just disappeared for me. Yeah, Meha, go ahead.
Yes.
If you can catch
Can
that.
you suggest a way to architect a data synchronization flow that updates the UI with each state and some intermediate states that might need user input?
Yeah, of course. That's what we are essentially trying to do here with the space library sample. And it really helps to conceptualize both data layer interactions and user interactions as events. So you might have events that look something like this. A user clicks a button, you might call that a load data event, and you would pass that event along to the view model and the state reducer. The state reducer might output something that says, okay, show a loading state. Meanwhile, the interactor has already started to load the data asynchronously. Once the interactor is done, the interactor can then come back to the reducer and say, I have a new event for you, which is that the data loaded successfully or there was some issue with that loading. And once that event comes through, the reducer, depending on how it's built, would say something like, okay, now show the content or just show an error representation. So it really kind of helps to think about the different stages that occur when a user performs an interaction. In most cases, a user interaction is what leads to a data layer interaction. So to summarize this example, user clicks, load image, reducer says, show a progress bar. Sometime later, interactor comes back and says, show the content that I loaded. And the reducer says, okay, I can show the content that was loaded. So that's what we found was really useful to construct it that way. And this made it completely agnostic for whatever type of rendering you might be using. So yeah, if you're curious about like what that actually looks like in detail, please check out the sample projects.
We have another question. Would the Tinder architecture be easier to refactor towards a declarative architecture, or would be easier for new features and let them coexist? I think the answer is coexist for now.
Coexist is for sure. I think it's once you embrace the idea that rendering is just an implementation layer detail, it's agnostic of imperative or even declarative, then that question might no longer apply, because it's perfectly fine to have imperative declarative coexist, because you've done the work ahead of time to compile the data that's needed. So it doesn't matter if it's an Android view or composable, either should work. So the goal, I would say, is, right, if you're making a new feature, if you add a new component, and you would anticipate adding or including or replacing it with a declarative component, just make sure that everything that either rendering idea needs is available to you right before you render.
Also, to add, I think if we just consider the Tinder architecture in general, we kind of play around with a lot of different architectures. Like we kind of follow UDF, we have state machines, like everything, which is kind of preparing the app towards declarative approach. If we kind of isolate the presentation layer, like we discussed in the presentation today, then I think we can like step up converting our app into a declarative UI. And I think there's one more question.
Yeah,
Sorry,
sure.
go ahead.
Yeah, go ahead. No, yeah, go ahead, Meha.
Which is the test tool we can use to test both the compose to test sorry which is the test tool we can use to test the compose? Is something like espresso or roboelectric?
I think Compose has its own like incredible testing framework, and we haven't included any tests in the sample project, or although we are looking to. And yeah, like I would encourage you to look into. I think the Android docs have a very separate section for how to test your composable specifically. And of course, it's probably way easier to test a composable than an Android view. And yeah, it's from what I've seen in the Compose sample apps and all that stuff. It's very seamless. Unit testing composables.
Yeah,
Cool.
that is all.
All
Thank you
right.
so much. Oh, yeah.
Thanks for. Oh, is anything else pop up?
No, it's like,
All right.
thank you. Yeah, it was a great talk. We have no further
Cool.
questions.
Sweet. So, well, before we sign off, we do want to mention that if you're interested in learning more about Tinder, feel free to join tomorrow's panel at 1:10 p.m. Pacific time. It's going to be hosted by one of our Android EMs, Marcos, and we'll have some senior Android engineers from Tinder, OkCupid, Hinge, and plenty of fish there to talk about some cool stuff. So yeah, and as always, if there are any more questions or any tips or any feedback, definitely do reach out to us. We're available on Kotlin Lang, and we're also available on Talk during the conference. So that's all. Thanks, everyone.
Thank you so much.